This webcast continues discussing some problems that involve linear momentum and the impulse momentum theorem. So I'm going to begin here with number 5. We're talking about a baby stroller. The force on this stroller increases at a constant rate from 0 newtons to 88 newtons over a period of 75 milliseconds. The mass of this baby stroller is 7 kilograms, and it is initially at rest. And we'd like to know what is the speed of the stroller after the 75 milliseconds of force has been applied. Okay, so we know that the impulse on this stroller will cause its momentum to change. But the first thing that I need to do is to calculate the amount of that impulse. And there are really two approaches here. So let me show both of them because I think that it's good to understand. So two approaches to finding the impulse. Well, I spelled impulse wrong, but you get my idea. So the first is, I could say, okay, the average force, since it says it increases at a constant rate from 0 to 88, would just be the average of that. So 0 plus 88 newtons divided by 2, the average force is probably 44 newtons. Well, then the impulse would be that average force multiplied by the elapsed time. So it would be the 44 newtons times the 75 milliseconds. Remember, you need to write that as seconds, so that would be 0.075 seconds. And so that would be 3.3 kilogram meters per second. That's the amount of the impulse. Let's see if I can also find that by a second method. We've also talked about how if you have a force versus time graph, that the impulse equals the area under the graph. Or in other words, the area between this graph and the x-axis. So here, if the force began at 0 and it went to 88 in 0.075 seconds, that red triangle would represent the amount of the impulse. And so the impulse would be half of the base times the height, which is half. The base is 0.075 seconds. The height is 88 newtons. And so once again, I get 3.3 kilograms meters per second. So whichever way I think about this, I get the same impulse. Now that I have that, I'm going to go to the impulse momentum theorem, which tells me that the amount of the impulse equals the change in the momentum, which equals the mass times the change in the velocity. Actually, it equals the mass times the final velocity minus the initial velocity. And the thing I'm looking for is the speed at the end of the impulse, right? So I'm looking for the final velocity. So therefore, I could just solve for final velocity. The final velocity is going to be the impulse divided by the mass plus the initial velocity. And so I have 3.3 kilogram meters per second divided by the 7 kilograms plus the initial velocity, which was 0 because it started at rest. And so therefore I get 0.471 meters per second. Okay. Let's look at another example. Joanne is traveling in her car at 85 miles per hour when the car hits a barrier. the bag deploys. It causes Joanne to stop moving in 0.22 seconds. Now, they're giving me a number here in miles per hour. I really need to convert that to standard units, so 85 miles per hour. And they're telling me that 1 mile is 1609.34 meters, and I know that 1 hour is 3600 seconds. So in standard units, that would be 37.998 meters per second. Okay, so the first thing is I want to draw a force diagram for Joanne. So Joanne has a weight, which is the gravitational force that the Earth is exerting on her. And I could calculate that, but I know that that force is going to be balanced by the supporting force, the normal force that the car seat is exerting on Joanne. And then, assuming that, she's moving in a positive direction, I'll just assume that, then the airbag applies a force in the opposite direction of the way that she's moving, and that causes her to stop very quickly. So that's an applied force on Joanne by the airbag. And that's going to be the net force in this situation. And then it says, determine the average force that the airbag exerts on Joanne. Well, the impulse momentum theorem tells me that the impulse, which is the average force times the elapsed time, equals the change in momentum, which is her mass times the final minus initial velocity. So the average force, that's what we're looking for, is going to be the mass times the change in velocity divided by that elapsed time. She has a mass of 60 kilograms. Her final velocity is 0 because she stops. Her initial velocity was 37.998 meters per second. The elapsed time was 0.22 seconds. That was just given to me, and that means that the average force is in the negative direction, so I get a negative number, 10,363 newtons.